all the different types of electrophiles possible. Same leaving group, I just kept it all as bromine. But all of this is to highlight primary, secondary, tertiary, primary allylic, secondary allylic, tertiary allylic, primary benzylic, secondary benzylic, tertiary benzylic. So how do I understand the term primary? Where does that come from? That comes from looking at the leaving group and the carbon it's attached to and how many hydrogens it's bonded to. So this first row, they're all primary. The carbon the leaving group is bonded to 2 hydrogens. So these are all primary. Now, they're a little different. This is primary. This is primary allylic. This is primary benzylic. The allylic comes from the carbon that's attached to the leaving group is next to a pi bond. That's the allyl group. The benzylic part comes from the carbon that's attached to the leaving group is bonded to a benzene ring. Still primary, right? The carbon that's attached to the leaving group has 2 hydrogens. But when that carbon is also attached to a benzene ring or a pi bond or an alkene, right, then it's either benzylic or allylic. Now these are different. These can form carbocations. Now why is it okay for this will never form a carbocation because there's not that many hyperconjugation buddies. If this form a carbocation here, there'd only be 3 hyperconjugation interactions. This is a primary, but when it forms a carbocation here, what can it do? It can do resonance. This pi bond can move over and help spread that charge out and stabilize it. And then in benzylic is even better. If you put a plus charge here, it's a primary carbon, but this whole benzene ring, all 3 of these pi bonds can help spread that charge out, make it even more stable. So this would be more stable than the allylic even. Benzylic would always be more stable than allylic. These other ones, so what's a secondary? Would mean the carbon that's attached to the leaving group is only bonded to 1 hydrogen. So these would all be secondary. Of course, this would be secondary and allylic, secondary benzylic. Now this carbocation would be more stabilized than this one because this one has all the same resonance this has, but then it also has what? 3 more hyperconjugation buddies. Sigma bonds 2 bonds away. So this secondary benzylic would be even more stabilized than a primary benzylic. Yes? Now tertiary, notice how the carbon attached to the leaving group has no hydrogens bonded to it. So these would all be tertiary. Tertiary allylic. Tertiary benzylic. Tertiary benzylic is going to be more stable than a secondary carbocation benzylic or primary carbocation that's benzylic because this has 6 hyperconjugation buddies plus the benzene ring stabilizing it if it was forming a carbocation. Could you do an Sn2 reaction on this? No, because it's still tertiary. You can't do Sn2 reactions on tertiary. Why? Sterics. You can't get to sigma star. These get a little tricky, right, when you form carbocations because these can do resonance structures. They're not rearranging. These are doing resonance structures. Now here's an easy tip. Benzene rings are really stable. So the likelihood that this pi bond is really going to move is not that high. I mean, it's going to stabilize it, but it's going to actually not have a benzene ring at the end. It'll always have a benzene ring at the end. These allylic ones, though, these ones, the resonance structures will move. We practice that. We'll keep practicing that. That was in workshop number 6. We did some problems like that. We'll keep practicing those. So be careful with the allylic especially of that pi bond resonance forming another possible carbocation that might react. Be careful with the resonance structures with these. And anytime you form a carbocation, you got to worry about rearrangements.